Now we'll look the flammability diagram. So we'll see the this is the flammability diagram. So we'll see that what does it contains and why it is necessary for any tankers. You should understand what does it mean and what are the specs of this and what are the uses of this. So basically, the flammability diagram or the flammability composition diagram is the one of the important document used across the world to understand the prevent of the fire and explosion. So if you don't understand the anything with any properties of the cargo and what are the your LEL and the UFL, so we sometimes call the upper flammability limit UFL also, UL also upper explosive limit, lower explosive limit, lower flammability limit. So these are the, you can see that the mixture, they are the mainly used for the hydrocarbon mixture and so a key to the cargo and the ship safety on the tankers. So on tankers, basically this is the important part. So it is essential on board the tankers follow certain procedure based on the studies from the flammability graph of the hydrocarbon mixture. So flammability diagram explain to us the how the gas or the mixture of two gases will behave and catch fire with the dilution other gases on the air. So the fire safety. So fire safety is the key to the successful operation of industry, including the shipping. A detailed discussion and the planning are required on tankers. A type of ship to avoid any mishap, proper tank cleaning, loading, and discharging procedures to be followed to avoid the fire and explosion. It needs only air, heat source, and the fuel to start fire. These three components are always available on board ships, and risks are high with the tankers. So on tankers, fuel is always present in a large quantity in different holes, and the air is present everywhere, and the heat source can be from hot work to a spark due to the static discharge. Removing any side of this fire triangle, air source, fuel, we can prevent the fire on board. So basically, the fire tangle, that is the fire tangle, why, how the fire can occur, and what is the reason behind the fire is occurring in anywhere or any states. So the basically the fire, the occurring of the fire is generally done when the fire tangles will have the all the elements. So like the oxygens, like the air source, and the any fuel. So when these three elements will be there, so three elements can be of any types or any forms. So fuel, that fuel, any fuel that will catch the fire if the source and the air are present with that area. So any fuel like a fuel itself, even the wood can also that you can call as the fuel. Coal also can you can call as the fuel. Petroleum product that also comes under the fuel, or any gases, chemicals, so which have the properties to catch the fire. So if we remove any of them, so we can stop the fire. But just imagine that in the cargo, so we cannot remove the fuels, we cannot remove the cargo itself, but we can remove either air or either the source. The source of ignition, how we can remove? So source of ignition, we can remove, we can minimize the hot work near that. We can minimize, we can mm, have we can protect the any ignition or any things which can create the fire, so that can be protected, so that can help that generally helps in the when we are doing the. So when you remove any source, so at that time you can have the you can protect the fire. So and also that when you remove the air, so how we can remove the air? So we can cut off the air supply, we can cut off the, we can minimize the presence of the air. So one is the when we ventilate we sorry we when we cut up the any supply of the air into the tank, then that time we can protect the cargo to catch the fire. And another is that we can introduce the inert gas also. So in the tanks, so if there is any presence of the hydrocarbons are there. So if the sufficient when we introduce the hydrocarbons, so there will be no any space left, and the oxygen quantity we know that in the inert gas the oxygen quantity is the less. So there is less than the sufficient amount of oxygen which can create the which can catch the fire. So that's why we generally introduce the inert gas into the tank. So what are the basically the flammability diagram is that, so you can see that inert gas is used on board that to remove the one side of the fire triangle. That means the air by pumping in inert gas in the tanker's hold to keep oxygen level at a minimum. So flammability diagram are used to understand the tank's atmosphere and help predict how much the oxygen to be maintained at all times. So these are the flammability diagram. So this is the flammable region. So you can see C, E, D. So these parts are the flammable region. So in these parts, so when there will be, so you can assume that you can put the any. Suppose you put the pointer with the any point, and if this regions, there will be the like x-axis is showing the percentage by volume of the oxygen, and the y-axis showing the percentage by volume of the hydrocarbon gas. So if the amount of the oxygen is sufficient and the presence of the hydrocarbon or gases are there. So if in this, if in your gas, your presence of the oxygen and the presence of the hydrocarbon is coming in this region, so there will be a chances there will be the this comes under the flammable region. So in these regions, if it is coming, so it will catch the fire, it will have the explosion, it will have the fire. But beyond that, so after the D and the before the C, so these are the before the C, these are the LEL. So these are the LEL, and after the D, these are the LFL. So UFL. So upper exposure limit, these are the lower exposure limit. So you can it can be also called as the upper flammable limit and the lower flammable limit. So below that there will be insufficient amount of the property or the insufficient amount of the both, because only if oxygen is there then there will be no any cause of the fire. So you can see when you in this position A to C. So A to C, yes, of course, oxygen levels are there, but the presence of the hydrocarbons are very less. So there will be no any, because in the fire triangle we have seen that there should be the fuel, there should be the any medium like spark or anything, any source of the ignition, and the third one is the air. But here is the percentage of the hydrocarbon is less at this position, so that's why the fire cannot be, the flammable region cannot be fulfilled, the fire cannot occur. Same like here also, you can see that if the presence of the oxygen, if you point any place over here, so what will have? It will have the less percentage of the oxygen. So if the less percentage of the oxygen is there, then also there will be no any fire. Even you go over here also, there will be the less percentage of the oxygen. So what does the flammability diagram means? So you can see the flammability diagram is the key element for planning safe cargo operation on board the ship. The diagram itself varies for different hydrocarbon gases. So we must understand how to read and understand it. For example, we get the lower and upper flammability limit of 1% to 10% based on the flammability diagram of for crude oil. So here is the line AB represent. So line AB. So these are the line A and the line B. These are the line A and A to B. So these lines represent the mixture of oxygen, air, and the particular hydrocarbon gas. Anything that is left to the line AB represent the condition where inert gas is also mixed with the hydrocarbon air gas mixture. So the gas mixture represented by the AC. So gas mixture you can see that represented by the AC. So these are the A to C. On the line AB is too lean to catch the fire, while DB is too rich mixture to get fire. So I have already seen this is the AC. So in the AC, it is too lean to catch the fire, and like the B to D, D to B. So this is the too rich to catch the fire. So now according to the diagram, when we go left to the line AB and inert gas to the tanks, so there is a sudden change in the tank atmosphere. Similarly, the upper and lower flammability limits changes with the more and more mixing of inert gas. Finally, the upper flammability limit, the maximum amount of hydrocarbon gas to air mixture which can sustain fire, and lower flammability limit, the minimum amount of hydrocarbon to air gas mixture with which can sustain the fire meet at a point represented on the diagram as point E. So this is the point E. So I have already shown this is the extreme point. So below that there will be no any flammable range. So below, after that, so there will be no any types of the fire or the explosion will take place. So this is the extreme, you can say extreme point of the flammable range. So what is lean or too rich mixture? So in a hydrocarbon air gas mixture, when it is too rich in fuel to burn is known as the too rich mixture. Hence the amount of the oxygen required to sustain the fire is absent, making it impossible to catch fire. Such an atmosphere can be easily tested on board by using the tank scope. So tank scope is basically the analyzer, the meter. So we can tank scope is used to check the tank atmosphere, so how much the presence of the hydrocarbons are there and the oxygens are there. So on another hand, when the amount of the hydrocarbon air gas mixture is too lean to catch fire, the mixture is called the lean mixture. On board, a special equipment called the explosimeter is used to detect the presence of the hydrocarbon in such an atmosphere. So, explosimeter is also the equipment that is used to measure the presence of the hydrocarbon in any compartment or any area. So, understanding the cargo operation on flammability diagram. So, inert gas is pumped into the tank while and after the successful cargo operation. On the flammability diagram, it can be seen as the decreasing gap between the UFL, upper flammability limit, and the LFL, that is the lower flammability limit. The UFL and LFL meet at point E, but the inert gas is pumped in until it reaches to the point F represented on the diagram. So now that during the cargo discharge, if the tank atmosphere is diluted with the air oxygen, it will allow a dangerous path FA. From the diagram itself, we can see that the path FA pass through the flammable range, and so it can be hazardous. So to avoid such a scenario, inert gas is purged into the tank before and during the cargo operation discharging. So generally, during the discharging operation, we are introducing the inert gas, generally the purging into the tank, so that there will be no presence of the hydrocarbon and there will be no any presence of the oxygen, so that it can catch the fire. So by purging the inert gas into the tank, oxygen hydrocarbon mixture is taken to point H from the F. No any further dilution with the air while discharging won't cause any risk to the ship. As the line HA represent on the flammability diagram don't pass through the flammability range. Now, suppose for some reason the tanks are filled with the less inert gas than the required, then during discharging it will miss the flammability range by a small margin. On the flammability diagram, it can be seen as the line GA, which goes almost touching the flammability range. This is called the critical dilution. The minimum amount of inert gas required to ensure the hydrocarbon mixture don't go into the range of the flammability region. So we will understand these all the things in the video also, that how actually it works and what are the actually it means. Now this is the conclusion part. So flammability diagram are an important document used to prevent the explosion on board the ship. An explosion can occur within the boundaries of the flammability zone in the diagram also. So it is important to know that understand that diagram prevent fire hazard. The flammability diagram shows us that the presence of the inert gas in the cargo holds don't guarantee safe cargo operation. So unless the amount of inert gas is always above the critical dilution limit, it is well understood that any amount of oxygen below 8% in the hydrocarbon air gas mixture is not threat. But to ensure the proper safety of the ship, it is capped at the 5% at all times. So these are the flammability diagram all about. So we will have the look about the video also of this flammability diagram.
cause hell lot of a fire. Fire hazard during a tank operation in vessel poses a major risk to the seafarer community. So guys, in this video we are going to discuss about flammability diagram and its basic understanding. So guys, let's go to the video. Cargo operation in tank involves a lot of pre-planning and discussion to prevent any kind of accident or mishaps. Proper procedures are followed during loading, unloading, tank cleaning and even man-entry time. It is known that for any fire to start, it requires a minimum presence of three components, that is air, fuel and source of heat in the correct proportion, which are the three major sides of the fire triangle, as we are already familiar with the fire triangle. In a cargo tank or vessel, cargo can play the role of fuel and complete one side of the fire triangle. Any spark, heat from the adjacent compartment or from the hot work or even atmosphere heat can act as a source of heat in the tank. The atmosphere air containing 21% oxygen serves to provide sufficient oxygen for the fire triangle to complete and a fire hazard to take place. Removing any one side of the fire triangle will be an effective step to prevent fire hazard on board a ship. But the question is, which side of the fire triangle should be removed? So the best possible way is to remove the air part of the triangle, that is the oxygen. We can remove it by simply inerting the atmosphere of the tank. Inert gas, which inert the atmosphere of tank by keeping the oxygen content to a minimum, which breaks the fire triangle. The oxygen content in the inert gas is about 5% and minimum oxygen concentration required for the combustion is 8% on board a ship. To be on the safer side, the oxygen content in the inert gas is usually kept at 2 to 3%. To study any tank atmosphere on board a ship, flammability diagram is very important tool. So guys, this was the basic introduction. So guys, let's go to the flammability diagram. So this is the flammability diagram. The x-axis represent percentage by volume for the oxygen and y-axis represent percentage by volume for hydrocarbon gas. You can see it very clearly guys. So guys, one more important thing is that percentage for the hydrocarbon which is required for the upper flammable limit and for the lower flammable limit is decided by the MSDS, that is Material Safety Data Sheet. Now what is UFL, that is upper flammable limit, that is the highest concentration of vapor or you can call it gas that will produce flash of fire when an ignition source, say heat from the adjacent bulkhead or arc or flame is present and it will produce flash. And what is LFL, that is lower flammable limit. It is the lowest concentration of vapor or gas that will produce a flash of fire when an ignition source from the adjacent bulkhead or from any hot work it will brought in near to that particular cargo or to that particular fuel, it will produce flash of fire. So between this particular limit the fire will occur, and above upper flammable limit and below lower flammable limit there will be no flash of fire, and above upper flammable limit and below lower flammable limit no flash of fire will occur, as the concentration of hydrocarbon above upper flammable limit is more and the amount of oxygen, that is the concentration of oxygen, is less in number. So these are not in equilibrium and not in proportion which complete the fire triangle. Such is the same condition below lower flammable limit. Here the percentage or the percentage of volume for the particular hydrocarbon is less and there is enormous amount of oxygen. So it will support the fire triangle and there won't be any flash of fire. So guys, before learning how to draw the diagram, let's first have a look at the line AB, which represents the concentration of mixture that include air and hydrocarbon gas only, that is this line. all the point to the left side of the line A, B includes inert gas in the mixture, and to the right side of the line AB and on the line AB doesn't include inert gas. One more important thing you must know is that if the oxygen content in the atmosphere is more than 21% by volume, then this particular flammability diagram is not valid. When inert gas is added to the tank atmosphere, the concentration inside the tank changes drastically. So does the upper flammable limit, and the lower flammable limit changes drastically. It can be seen from the diagram that the upper flammable limit and the lower flammable limit converges to the point E when the tank is inerted, or you can say that when inert gas is added to the tank. It can be understood that flammability range of a mixture decreases with the addition of inert gas. As we have already seen, as inert gas is added to the tank, the flammability range decreases drastically and it converges to a point E, as we have already discussed. Now let's assume a mixture of hydrocarbon gas, air and inert gas such that it is at a point F in the graph. If this mixture is diluted with air, that is oxygen concentration 21%, then the new concentration of mixture will follow a straight line drawn from F. Straight line drawn from F to the 21% mark on the oxygen percentage x-axis, that is line FA. So if oxygen is added to that particular tank or dilution with air is done, then it will follow this particular line, as atmosphere oxygen contains 21% of oxygen, which is clearly known to us. So it will tend to follow this line through F and reach the point A, which is the 21% of oxygen. It can be seen from the diagram that on diluting F with air, it passes through the flammable region. This is the flammable region, and when we dilute F with air, that is 21% of oxygen, it passes through the flammable region, and it is quite hazardous too, and we can't do such act on board a ship, as F will pass through the flammable region and it is a hazardous condition, and in the presence of any heat, and obviously there is fuel available as a cargo in the tank, and oxygen is abundantly available in the atmosphere, and if there is slight spark or any heat source from here and there, automatically it will complete the fire triangle and obviously fire will take place, as we already know it about fire triangle principle. To tackle this problem, what we can do is that we need to first purge the tank with inert gas. Since inert gas has O2, that is oxygen concentration of around 2%, as we have already discussed, the concentration of mixture during purging process moves through the line Fj, and J is the 2% oxygen concentration in the inert gas. So this is the 2% mentioned on the x-axis, percentage by volume for oxygen. The purging is continued till the mixture reaches the point H. This is the point H, and purging is done in such a manner that it reaches the point H, and from the point H further dilution of air is done, that is adding oxygen to that particular tank. If oxygen is added to that particular tank, what will happen? It will tend to reach the 21% mark on the x-axis, that is percentage by volume for oxygen. So you can see it will go like this and reach the point 21%, that is point A marked on the x-axis. So you can see very clearly that HA line doesn't passes through the flammable region, and it is not a hazardous process. Hence safe condition is maintained throughout this process. While looking at the diagram, we came across the term critical dilution line, that is GA. This is a critical dilution line. Let's try to understand this term. The line GA passes by just touching the flammable region portion of the diagram. So it just touches this particular region. If the mixture F would have been purged out such that less than H, so less than H is L. If it is purged in such a manner, then while dilution with the mixture, it would have passed through by just touching the flammable region. So you can see that it will be just be touching the flammable region if we dilute with oxygen from the point L. And we can clearly understand that critical dilution limit is the minimum amount of purging required to ensure that mixture doesn't fall in the flammable range while diluting with air. So we always try to do the purging in such a way that it is reached below L, that is to a point H. And after reaching the point H only, we are further diluting it. Or else if we dilute above H in such region of L, then it will pass through the line falling in the flammable region, and obviously it is a hazardous condition. So to avoid such condition, we purge in such a way that it almost reaches the point H, and then only we dilute it so that it doesn't fall in the flammable region. So we can clearly understand by this that the use of inert gas itself doesn't guarantee the safe environment of the tank during tank operation until inert gas is above the critical region. So we have to bring it below the critical region to a point near H. Then only it will be a safe and sound operation. So to be on the safer side, it is common practice to continue purging the mixture F beyond the critical dilution limit, that is the line L, to prevent any hazardous condition on board a ship in the cargo tank. So that's why we always try to purge the tank below the critical line and nearer to the point H, so that upon dilution with air, it doesn't passes through the flammable region and hence no hazard take place on board a ship. The flammability diagram is an important point to be considered while doing any tank operation. An understanding of the flammability diagram is very necessary to prevent any fire risk not only to oneself but also to the fellow seafarers. So guys, we should know this flammability diagram very clearly. Before ending this video, I have a question for you. So guys, why is this particular line, that is A, B, is not straight? It is not perpendicular in nature. Why is it so? If you can answer it, please comment down below. If not, I will be